Have you ever stopped to think about the massive gap you see between different historical timelines? On one side, you have accounts pointing to a history of maybe just a few thousand years. And on the other, you've got scientific methods giving us dates in the tens or even hundreds of thousands of years. Well, today, we're going to unpack one very specific model from our source material that actually tries to bridge this exact gap.
Okay, so let's get right to the heart of this puzzle. You've got the biblical timeline, which, based on the genealogies in Genesis, adds up to a world history of about 6,000 years. But then you have carbon dating, a total cornerstone of modern archaeology, which often gives us ages that are way, way bigger. So how could both possibly be true? According to the model we're looking at, the answer might be hiding in plain sight.
And here's the twist. The key, according to this model, isn't to argue with the physics of radioactive decay itself. No, instead, it challenges a single, fundamental assumption we make about what the ancient world was actually like. It's a really fascinating thought experiment, and it kind of flips the whole conversation on its head.
Right, so to really get what this model is arguing, we first need a super quick refresher on how carbon dating even works, because the secret, it says, is all on the starting point.
It's actually a pretty elegant process. See, as long as something is alive, a tree, an animal, you name it, it's breathing and eating, constantly taking in carbon from the environment. So it has the same ratio of regular carbon to radioactive carbon-14 as the atmosphere. But the moment it dies, that exchange stops, and that's when the carbon-14 clock starts ticking down, decaying at a perfectly known rate. Scientists can then come along later, measure how much is left, and calculate how long it's been since it died.
But, and this is the absolute key, that whole calculation hinges on one critical variable, N0. This is just a symbol for the amount of C14 a sample started with. Everything, every single age calculation depends on knowing or assuming what this initial amount was. And as you're about to see, that assumption is everything.
And boom, here it is. This is the central what-if question the source material poses. Mainstream science generally works on the assumption that the C14 ratio in the atmosphere has been pretty stable over time, with some known wiggles. But this model asks, what if it wasn't? What if, way back in the past, the world's C14 level was just lower, like a lot lower? So how does the source propose to solve this thing? Well, it doesn't just say the level was lower. It gets way more specific. It proposes a precise fraction that, it claims, makes these two clashing timelines suddenly click right into place. This is the core idea right here. The model says that if a fossil started with only 1/3 of the C14 we assume it should have, our modern dating methods would get, well, tricked. They would see that small amount of remaining C14 and think, wow, a lot of time must have passed. So a 6,000-year-old sample would look like it's tens of thousands of years old. And the model argues this isn't just a random number. It's a number they get by combining several factors. Yeah, the model doesn't just pull this 1/3 figure out of a hat. It actually builds a case by pointing to 3 separate environmental factors in the ancient world. And it argues that when you combine their effects, they mathematically result in this exact fraction. Let's take a look at each one of these levers. Okay, the first lever is all about timing. See, it takes a really, really long time for the amount of C14 being created in the atmosphere to balance out with the amount that's decaying away. This model argues that if the world is only 6,000 years old, the whole system just wouldn't have had enough time to reach that balance, or equilibrium. It would have only built up to about 52% of the saturated level we see today. Lever number 2 is a proposed physical shield. The source suggests that a canopy, which it ties to a description in Genesis, along with higher atmospheric pressure, would have acted like a global sunscreen, blocking a good chunk of the cosmic rays that create C14 in the first place. This, they calculate, would cut production down to about 65% of what it would be otherwise. And the third lever? That's dilution. The idea here is that the pre-flood world was way more lush, with a much bigger total reservoir of carbon. More plants, more life in general. So the C14 that was being produced would have been diluted in this much larger carbon pool, lowering the overall ratio of C14 to regular carbon by another 10% or so. And here is where it all comes together. When you take these 3 proposed factors and you multiply them, so the non-equilibrium effect times the shielding times the dilution, what do you get? You get a number right around 0.30. That's 30%, or, you guessed it, almost exactly the 1/3 value this entire model is built on. Okay, but wait a minute. Proposing a giant planetary shield, that's a huge claim.
and it runs smack into a massive scientific counterargument. Any kind of canopy like that would trap a crazy amount of heat and basically cook the planet.
And here's that objection, plain and simple. It's a really common and powerful critique you hear. A thick layer of water vapor is an incredibly powerful greenhouse gas. I mean, standard climate models tell us this would crank the heat up on the surface to well above boiling. Not exactly friendly for life.
But the source material pushes back. It argues that this objection is based on an oversimplified version of the model. It's like they're saying, hey, you're arguing against a simple water vapor-only blanket, but what we're actually proposing is something way more complex and stable. So instead of that simple vapor blanket, the source describes what it calls a composite infrastructure. This system would have included a layer of ice crystals, which are great at reflecting heat away, plus significantly higher atmospheric pressure, which adds mass for shielding without as much of a greenhouse effect. On top of that, it proposes a stronger magnetic field and totally different atmospheric patterns. The argument is that this whole system, working together, could give you the cosmic ray shielding you need without the runaway heat problem.
So what's really crucial here is seeing how all these different pieces, the math, the physics, and the response to the big counter-argument are all woven together. They form a single, cohesive story that attempts to line up with that 6,000-year timeline.
And this timeline here really lays out that story. It starts at creation, with a low C14 world protected by this complex shield. For centuries, C14 is slowly building up. Then comes the biblical flood. The windows of heaven open, the shield collapses, and the Earth's entire environment is changed forever. Cosmic rays just flood the atmosphere, and C14 production skyrockets towards the levels we know today. And that dramatic shift, in this model, is exactly why things from before the shift seem so incredibly old to us now. So let's just recap the whole hypothesis one more time, nice and clear. It really stands on three pillars. A system that hadn't reached equilibrium yet, a powerful shielding effect from a complex canopy, and the dilution of C14 in a much bigger biosphere. The model says each one of these contributes a specific mathematical factor, and when you combine them, you land on that crucial starting value of about 1/3 of today's levels.
And that brings us to our final question. This whole explanation has been a deep dive into one model's attempt to solve a puzzle by challenging a single starting assumption. And it really leaves us with a much bigger idea to chew on. If the world of the past was fundamentally different from our world today, how would that change the way we even measure it? It's a fascinating question about the assumptions that lie at the foundation of how we know what we think we know.